25H7G6. If you are looking for the answers of how to interpret this engineering fit designation and how to find tolerance values on hole and shaft, you are watching the right video. My name is Kevin Kutto and I will help you to get these answers throughout this video. Do subscribe to the YouTube channel and like the video and comment if you find it useful for you. Before we begin, I recommend you to watch another YouTube video on my YouTube channel, which is how to choose an engineering fit. Now I have explained everything about engineering fits and especially fundamental deviation diagram, which is needed to finalize tolerance on hole and shaft. Now link is provided above and also into the description. So without any further delay, let's begin. 25H7G6. So what are these 25, H, 7, G and 6 values are all about? 25 represents the basic size. Now what is the basic size? Basic size is the size of hole and shaft which are in engineering fit, and they are equal values before we apply tolerances on them. So why we apply tolerances on them? So that we get different engineering fits. So once we know the size of the hole and shaft is 25, we have to apply different tolerance blocks, combination of different tolerance blocks on hole and shaft to get different engineering fit. Now this 25 size can be anything. So it can be 40 also, 200 also, 100 also, 1000 also, no problem. So combination of these basic size and these letters and numbers is going to give us different engineering fit. Now what is this H all about? Capital letter represents the hole tolerance block. And specifically capital H represents that it is hole basis system. Now what is hole basis system and what is shaft basis system? I have already explained in my previous video. I will recommend you to watch that. But we have to understand that either we'll have capital H to represent hole basis system or we will have small h to represent shaft basis system. In this example we have capital H, that means we have a hole basis system here. So what is this 7 all about? 7 is a IT grade. Now what is the significance of this capital letter and what is the significance of this IT grade? Combination of basic size and this capital letter is going to provide us fundamental deviation. Now fundamental deviation is very important input which we require in order to finalize the tolerances. Similarly, the combination of this basic size and this IT grade is going to provide us a tolerance on the hole. Both these informations together going to help us to provide upper and lower limit on this 25 basic size to get particular engineering fit, specifically in this case H7G6. So what is G in this example? G is nothing but it is a tolerance block on the shaft. Now in this case we have a G tolerance block. If instead of G we have a small h tolerance block, then it becomes a shaft basis system. But in this case we have a G tolerance block. And 6 is the IT grade on the shaft. So now again this basic size and this letter is going to provide us a fundamental deviation, and this basic size and this IT grade 6 is going to provide us a tolerance on this. So we are going to need fundamental deviation and tolerance on hole, and we are also going to need fundamental deviation and tolerance on the shaft. Now how to interpret fundamental deviation diagram, how to understand these blocks in the fundamental deviation diagram, I have already explained in my previous videos. So let's go into the basics of fundamental deviation diagram. So here we have 25 as a basic size and 0 line is represented here. This is the line where we have fundamental deviation to be 0, and we have H block represented here because this is a hole basis system. So we know that in hole basis system our lower limit of the hole is touching here and H block will touch to this 0 line. IT7 is the height of this block, which is nothing but tolerance of this block. Similarly, we have a G block which is the closest block to this 0 line, and you can see here fundamental deviation is shown. So fundamental deviation is the closest deviation to the 0 line, and then we have tolerance block on G as well, so which is represented by IT6. So once we know the basic size, that means hole size and shaft size, and once we know the fundamental deviation, and once we know the tolerance, it's easy to find lower tolerance and upper tolerance on this basic size. For example, if we have a hole here, and if we know the basic size here, if we know that fundamental deviation is going to be 0, because it is a hole basis system, and we know that for hole basis system fundamental deviation is going to be 0. And once we know the tolerance, which is height of this, we can easily get lower tolerance and upper tolerance on 25. Similarly, for shaft also, if we know the fundamental deviation, that means how far this block is placed from this 0 line. If we know that, and once we know the IT6 grade tolerance, that means height of this, we can easily find out upper tolerance and lower tolerance on this 25 basic size. So our inputs will be tolerance and fundamental deviation for both hole and shaft, and our output will be upper tolerance and lower tolerance for both hole and shaft. Now before we go into the calculation part, we have to understand that all the charts are given in IS 919 or ISO 286 standard. Now we can directly find out the tolerance values using those charts, but I'm also going to show you some calculation part where how we can calculate those tolerance values which are given in the chart without looking at the chart, right? So we are going to confirm that. So this is the first chart we are going to refer. In this chart we have 18 IT grades which are given, IT1 to IT18, and then we have basic size ranges given. So if the basic size range is up to 500, then we are going to use the standard tolerance factor, which is nothing but I, this formula, right? And then if the basic size is more than 500, between 500 to 3150, then we are going to use capital I formula. Now how this formula is used, what is this D is all about, we'll see it later. Okay, but right now understand that there are two formulas based upon how the basic size will be. Similarly, you can see here there are multiplication factors, so 10I, 16I. So once you calculate the I, we have to multiply it by 16 in order to get the tolerance value for particular dimension. So that is the significance of this multiplication factor. But before multiplying it, we have to calculate small I or capital I based upon where the basic size will place. So let's begin with the hole first. We have H7 hole, that means IT grade is 7. So what I have to do? I have to use this chart, right? I have to look at this chart. So what is this chart? Where I have this multiplication factor. Now I had shown you what is I means. Okay, what is I means, and this was the multiplication factor. So once I know the size, which is less than 500, and once I know the IT grade, we can find out the multiplication factor. So in this case, we have a multiplication factor of 60. Once you know the IT grade, and once you know your basic size, range in which your basic size falls, you can very well predict, what is the tolerance. So our basic size is 25, so it falls between where? 25 falls here, not here. It will fall between 18 to 30, right? And what IT grade we have? 7. So IT grade is 7. So if you go here in this row, and if you go here in IT7, what is the tolerance we are going to get? 21 microns. So if you know the IT grade and once you know the basic size, you can directly find out this tolerance for the whole block from this chart. It's very easy. Now you might be wondering how these figures came, how they found out whether it is 21 microns, 13 microns, how these figures came. That's why I want to show you certain calculations. So in calculation, the first thing we have to find out is D. So what is D? You have seen this formula already in past. So what was the D? D is a geometric mean. D is a geometric mean. So how it is calculated? So for that you have to go to the range, right? So I know that my 25 basic size falls in the range of 18 to 30. So once I know the range, from this range I can calculate geometric mean size. So how to calculate? Just multiply them together and take the square root. So that is what D is. The geometric mean is equal to D is equal to 18 into 30, and that's how I am going to get 23.2378. Okay. Now once I calculate D, it's very easy to calculate standard tolerance unit, which is I. I is nothing but standard tolerance unit, and this formula is already given. So this formula is for when your size is lesser than 500, right? And I have already shown you, if size is more than 500, then we use capital I. Already you have calculated D here, you just put D and you can find out I. Now once you find out I, which is 1.307 micrometers, you have to use this multiplication factor. Now we know it is 7th grade, so 16 is the multiplication factor. So 16I means 16 into 1.307, and which will come to be 20.912 micrometers, and if you round them up, it will come to be 0.021 millimeters, which is nothing but 21 microns. So which is the same figure which we got here. So same figure you are going to get directly in this chart. So you need not calculate all these things, but I just wanted to show you how these things, how these tolerances are calculated basically, right? So these are calculated based upon these formulas, and this is how we have to calculate this tolerance. Now let's go and find out fundamental deviation, because these two things information we needed, right? Tolerance, and we needed a fundamental deviation. So here we can see, here we have H7 block here, okay? So we already calculated this tolerance, that means we know this height of this block, which is nothing but 21 microns, which is 0.021 mm, okay? Now I have to calculate fundamental deviation. What is the fundamental deviation here? 0, right? But still I want to show you how we can find it out. So we have already seen this table where capital A, B, C, D, E, F, G, H letters were there, right? And we can find it in ISO 286 or IS 919 standard. So if you know the range in which basic size fall, which is 25, falls between 24 to 30, and once we know the letter capital H, you can very well find out fundamental deviation at the cross section, so which is 0, which makes sense, right? Yeah, so once we have fundamental deviation here, then it's easy to calculate the lower tolerance and upper tolerance. So what will be the lower tolerance here? Lower tolerance will be 0, right? Because fundamental deviation is 0, that means lower tolerance is 0. And in that, if you add this height of the block, which is nothing but tolerance, you are going to get upper tolerance. So upper tolerance will be 0.021. So, and this was your basic size. Basic size was 25. So that's how you are going to get limits. 25, lower limit was 0, and upper limit is 0.021. In case of shaft, we have, what is the IT grade here? 6, right? So for IT grade 6, we have to use 10I as the multiplication factor. Now obviously size is below 500, so that's why we have to use that small I formula. If it is more than 500 basic size, then we have to use capital I formula. You already know that. So again, the same, we have to see in a IT grade 6, and we already know where this will be. So the basic size falls into this 18 to 30, right? And if you go here, you are going to get tolerance directly, 13 microns, right? So let's calculate it and verify. So we have already seen this calculation also. D is same because the range is going to be same. So it is same thing which we calculated for hole. I is also going to be same because D is same, that means I is also going to be same. The only thing which is changing is multiplication factor. So we have 10I, that means I we calculated 10 into 1.307, which is coming to be 13.07 microns, which you convert, it will give you 13 millimeters if you round up, okay? So which we got here. So do you have to do these calculations? Obviously no, you can directly find this tolerance in this chart. Now once you do find out tolerance, what is the next thing you want to find out? Fundamental deviation, obviously, right? Because now what we did, we found out H, we also found out lower limit and upper limit, right? Lower tolerance and upper tolerance, we have already found out that. Now we have G block here. G block's tolerance also we have found out, right? Which is nothing but how many? 13 microns or 0.013 millimeters, right? Now what we have to find out? We have to find out fundamental deviation. So once I find out fundamental deviation, I can easily find out, calculate lower tolerance and upper tolerance of this shaft. So let's begin with G Where is the G? G is here, and we have 25. 25 lies here. So if I go down from here and if I go down from here, I'm going to get a fundamental deviation which is -7, and which makes sense. It is minus because it is below the 0 line. So 7 is nothing but it is in microns. So 0.07 millimeters. We have to divide it by 1000. So that's how we convert microns into millimeters, 0.007. So once we got this fundamental deviation, now very easy to get upper limit and lower limit. So what will be upper limit here? The upper limit will be 0.007, right? Minus 0.007. It will be minus because it is down, right? It is reducing this 25, right? So it has to be obviously down. It is reducing this 25 basic size. Now we reached here. So from this minus 0.007, you have to minus 0.013 to get a lower limit. This was upper limit. Okay. So lower limit will be what? Minus 0.007 minus 0.013, which will come to be 0.020. Correct? 0.020. So same thing which we'll find out here. So if you calculate here, same things are there. Fundamental deviation is -7, which is nothing but 0.007 millimeters. Then we are going to get this limits, right? So you can see 25, which was our basic size. Upper limit was 0.007 minus, and then lower limit was 0.020, which we already found out. Let's summarize it. So this is a summary what we had shown earlier also, but now we have figures. So lower tolerance is equal to 0, upper tolerance is 0.021. Similarly, we have minus tolerances because fundamental deviation is minus. This is minus, okay. And if you put this into the hole and shaft, 25, 0 is the lower tolerance plus 0.021 and 25 both are minus, okay. So that's how we got the tolerances on hole and shaft.